For a one-dimensional bar element, we will now derive the element stiffness matrix. We know that the potential energy is given by pi, which is equal to strain energy plus the work potential. The strain energy is given by half integral over the length L transpose of stress into the strain into A dx. The work potential can be due to body force, due to traction force, and due to a point force. So that is minus F integral F ut A dx minus integral u transpose into T ds, which is the surface, and minus summation I going from 1 to n ui pi. So this is the body force term, this is the traction force, and this is the point force. That is a work potential due to all these three factors. Now the strain energy UE of the element is given by the first term in the equation above. Let me rewrite it and label this as equation 1. We know that the stress is given by E into BQ. Since we have used small q for displacement, I will put q term here. You could also write it as u. It means the same. Epsilon is given by B into Q. So we get the strain energy after substituting these terms as. Now when we have a matrix A, say it is equal to B into C, if I want to get the transpose of the matrix multiplication rule is it will be C transpose into B transpose. So using the same, I get Q transpose, B transpose, E is constant. Okay, so epsilon is B into Q into A dx. This I will call equation 2. Now getting the QT term out of the integral sign, we have B transpose I'm just rearranging the terms. So in the finite element model, the cross-sectional area of the element E denoted by A is a constant. Also B is a constant matrix. Now when we want to convert from x to zeta, okay, we will get dx equals to x2 minus x1 upon 2 d zeta. This comes from the equation which relates zeta to x. So when we differentiate, we get this, and we know that zeta varies from minus 1 to plus 1. Okay, let us call this equation 3. The equation 3 can be rewritten as dx equals to x2 minus x1 will be nothing but the length of the element. So LE represents the length of the element. Now in some textbooks you will see that the area of the element is represented as AE and L is represented as LE. So don't get confused with that. Substituting this again in the equation of strain, we get So we have half Q transpose B transpose Young's modulus into B matrix into A. Integral of zeta, integral d zeta is zeta. Dx will actually turn to Le by 2. So this has to have a term Le by 2 here. So this is Q Le by 2. On substituting the values, the upper integral and the lower integral, so it will be plus 1 minus of minus 1, which is 2 Q Le by 2. And in the textbooks you will find E, that is Young's modulus, written as E suffix small e, which means the Young's modulus of the element. So this 2 and this 2 gets cancelled. So we have Q transpose B transpose Young's modulus B into A Le by 2 into Q. I will label this as equation 4. We know that B matrix is given by 1 upon x2 minus x1 minus 1, 1, or x2 minus x1 is nothing but the length of the element. This is a 1 by 2 matrix. So B transpose will be given by the rows interchange into column, and this becomes a 2 by 1 matrix. Now we need B transpose into B. So we get, this is minus 1 into 1 upon Le minus 1 into 1. Now this is a 2 rows 1 column matrix, and this is 1 row 2 column. So the columns of the first matrix matches the row of the second, and the resultant matrix has to be of size 2 by 2. So 1 by Le square. So we multiply these terms and we get a 2 by 2 matrix. Now we can substitute it in the equation of strain. So we get Q transpose Young's modulus. A is the area of the bar, cross-sectional area, and B by B transpose is what we have just obtained, multiplied by Q. Now 1 Le here gets cancelled, and the equation now is half Q transpose A E by Le 1 minus 1 minus 1 1 into Q, or we can also say it is half Q transpose the stiffness matrix of the element into Q. Okay, this is why the Q terms from the beginning of the derivation, you see that I have rearranged it as Q transpose at the left hand side and Q at the right hand side. So the equation that is in the middle of both this gives us the stiffness matrix of a bar element. Okay, so Ke is nothing but Ae upon Le 1 minus 1 minus 1 1. This is what we wanted to derive. Okay, it is the stiffness matrix of a bar element, and this is going to be used for solving problems. Look at the size of the stiffness matrix. It is 2 by 2. Okay. So we have, for a bar element, we have two nodes, node 1 and node 2. The degree of freedom is, each node can move in one direction. So this can move in one direction and this can move. So the degree of freedom is 1 plus 1, which is 2. So the size of the stiffness matrix equals to a square matrix of 2. Okay, that is why we get here 2 by 2. In the next lecture, we will talk about the force terms, that is the body force, the traction force and the point force.